Hello everyone, I'm Kshitij Kumar. This is our work for Interspeech on one-dimensional row convolution LSTM. This is fast streaming ASR at accuracy parity with LC BLSTM. My colleagues are Chaoshun, Ifan, and Jian, all from Microsoft. This is an outline of our work. We are going to introduce this work on row convolution LSTM in the context of ASR matrix, which are accuracy, latency, and cost. We want a highly accurate model at lower latency and lower cost. Next, we provide an acoustic model overview of the current state-of-the-art models like uni-LSTM, bidirectional LSTM, and LC BLSTM models. From there, we develop a new problem scope with respect to above ASR matrix. Then we develop a row convolution RC-LSTM model, and our objective is to seek accuracy parity with LC BLSTM model and offer lower cost and lower latency. Then we discuss some of the model attributes like self-attention initialization and some connections with other work. Finally, we discuss our experiments and results. Now, for a large scale ASR system, high accuracy is the most desirable. We want the ASR system to be robust to seen and unseen acoustic domains and acoustic environments. We want the models to generalize well across speaker accents and across dialects and genders. So this is very challenging for ASR, and that is why we need to build a sufficiently robust model and sufficiently complex model to handle all the diversity. Furthermore, low latency is also very important for ASR. The consumers expect a fast streaming ASR response. This is especially important for applications like video captioning and web search and dictation applications where prompt response is very much critical for user satisfaction. The other applications like keyword detection are also important for low latency scenarios. Beyond that, to serve ASR at scale, we want the models to also have smaller size and lower cost to compute. Next, we do an overview of the current acoustic models like uni-LSTM model, which is widely used as AM structures in a large number of applications. LSTM cells build memory, they control the flow of information and address vanishing gradient problems. And these have been applied in many applications and have shown to be substantial improvement over prior models in DNN models. The good thing with LSTM is that there is no requirement for a look ahead. So these models are fast to compute depending on the size, and they can offer a faster response. A built up on the uni-LSTM model is a bidirectional LSTM model. They have a sequence of forward as well as backward LSTM layers. And as is understandable, the latency for the bidirectional LSTM is longer. But it also comes with a much stronger accuracy than an LSTM model. And the size of the model is typically twice X of uni-LSTM model. Beyond that, we also have a latency control LSTM model that tries to address the latency aspect in BLSTM model by restricting its computation to batches of data as shown in the figure. Now, this is a quick summary of the matrix that we discussed and the acoustic models that we presented. So here the check mark indicates the models that meet our expectations. For example, the LSTM model has weaker accuracy, but the compute cost and the latency is stronger. The LC BLSTM model and the BLSTM models have stronger accuracy, but they are not as fast as a LSTM model. Though LC BLSTM model is little better in terms of latency in comparison to BLSTM model. And the purpose of this work is to develop a new model with the row convolution LSTM model that satisfies all these expectations. Now, we know that speech is a highly contextual signal, and due to the physical movement of the articulatory organs, the spoken content has a dependency on the previous as well as future content. And because of that, a key learning that we also developed from the BLSTM model is that we want to be able to use some future information in the models that we develop. And the key direction of our work is to be best able to leverage future information in the context of uni-LSTM model to keep the model structure simpler and easy to compute. And next, we'll propose an RC-LSTM model. Now, this is a quick description of the RC-LSTM model. This builds on a simple uni-LSTM model structure. And the key motivation for RC for our work is derived from a prior work in Deep Speech 2, where the row convolution operation was proposed, and it was integrated with the in the model presented in the Deep Speech 2 work. Here we borrow the core RC operation and apply that to a purely uni-LSTM model. And we also simplify and develop and extend the work in numerous directions. Now, as shown in the figure, we show two layers of LSTM, L and L plus 1. And in between the LSTM cells, we have connections. The output of the Lth layer goes to the L plus 1th layer. And the connections are through the one-dimensional convolution operation. Now, we would like to highlight that in this operation, the particular output, for example, the kth output of the LSTM layer L is connected only with the kth input to the next layer. There are no cross connections here. We'll further discuss this. Now, when we apply this row convolution operation, we can apply this work to at different stages, for example, to the features or hidden layers or the top layers. Next, we present some attributes of the model. The model is small, as we can see that the only new parameters in comparison to a uni-LSTM model are the RC operations, which are and which there are no cross connections there. So the model structure is very simple and new parameters are minimal. The model is very simple. It just requires two operations, RC operation and LSTM operation. And we can also see that the model also has an inherent time and frequency factorization, which leads to effective training, and it can be very important for AM adaptation purposes. The reason why we refer to this time and frequency factorization is that the LSTM cells, for example, layer L or L plus 1, they do not have any future information. And all the future information is abstracted and computed, and all the dependencies are inherent only at the RC operation. So that is why we say that it has time and frequency factorization. This work also has some parallels with prior work in TDNN model or CLT LSTM model, but our work, we believe, is the first to achieve parity with LC model. We also in our work, we found it important to carefully initialize the row convolution parameters. The typical initialization is to choose a small value in a range of negative 0.5 to positive 0.05. However, in our work, from our study, we recommend the alpha parameters, alpha parameters to be 1 for the alpha 0, k parameters to be 1 for all k and L. This leads to very desirable self-attention behavior in the model and leads to faster convergence as well as more accurate models. Next, we describe our experimental setup. All the data that we work with is anonymized. We work with a large variety of data, and we have two setups: medium task 6,000 hours and large task 60,000 hours of data. The data spans our applications in close talk, far talk, natural conversation, command and control, dictation, and voice search and call center, etc. The hybrid acoustic model that we built has 6 layers LSTM with 1024 cells projected to 512. The model has about 9,000 acoustic states with 25 millisecond core features with 10 millisecond shifts. We also apply frame skipping for faster evaluation. The features are 80-dimensional log-mel filter bank features that we also concatenate to 160-dimension feature to fill in missed frame in the frame skipping. Our language model has 1 million words with 5 gram LM. In this work, we will report word error rate as well as algorithmic latency in milliseconds. And to clarify, each future frame that we refer to will require a 20 millisecond latency because of frame skipping. We first report results on a medium scale task. Our baselines are the model A and B there, 80 dimension and 160 dimension. We clearly see that model B with 160 dimension feature has a stronger word error rate. And that is our effective baseline. And in all the work, we use 160 dimension features. So before presenting RC1 model, we also present a model C where we build on the model B, but we include 6 future frames, concatenate 6 future frames at the input layer. So clearly that improves word error rate from 14.2% for the baseline B to 13.4 for the model C. So it clearly shows that there is some information or some extra benefit we can get by using future frames at the input layer. However, RC1 is a proposed work where we apply the row convolution at all the LSTM layers, and we equally distribute six feature frames, that is one frame at each of the hidden layers. And we get a much stronger 12.9% word error rate in this work. So we also developed this work to RC2, 3, and 4 models, where we respectively use 2, 3, or 4 future information frames in the row convolution operation at all the hidden layers. And we see a gradual and consistent improvement in word error rate. Along with that, we also report latency numbers there, so the latency will also increase. So in the prior work, we found that distributing the look ahead to all the layers is effective. We conduct a similar experiment in the RC model structure, where we keep all the look ahead at either the top layer or the upper 3 layers, equally distributing them. In total, there are 6 future frames being used. So we also see that the RC1 is a still better choice. That is, we get stronger results by equally distributing future frame information to all the layers. We also report these results on a larger scale evaluation, the 60,000 hours of data, and we clearly see that the LC BLSTM and RC LSTM model have a close accuracy parity. Finally, we report some results on the AM adaptation, and we see that we conducted an experiment on a small room and a medium room task. The medium room has larger reverberation, and we report these results for an RC2 model. And there in the chart, we plot the values for the baseline, that is we refer to as the clean model, unadapted model, and we refer to we plot the alpha values for at different LSTM output indexes for the models that we adapted on small and medium rooms. What we note here is that there is a trend. That is, the alpha values are clearly distinguishable for clean, small, and medium rooms. In particular, these alpha values here trend towards the lower side. And the implication is that the model parameter can be used to gauge or test the room reverberation by following adaptation and looking at the alpha parameters. Here is a summary of the work. We created a new problem space within the constraints of ASR matrix we described before. And we also noted that using future information is a key learning from complex models like LC BLSTM model, and we build along that. We proposed and developed a row convolution LSTM model by using simpler constructs. The model is very small, and it is simple to evaluate and to compute as well. We showed that the uniformly distributed look ahead to all the layers is the most effective approach. Overall, we achieved 16% word error rate over the Uni-LSTM model, along with a close parity with LC BLSTM model. We also showed that the AM computation cost reduces to about 50% compared to LC model, and in particular, the first intermediate latency reduces from 800 millisecond to 400 millisecond range. Along with the the intermediates will also have a very strong reduction in latency. So overall, the RC model shows a promising direction and achieves the results that we wanted to achieve. Thank you, and looking forward to your questions.